Okay, question number 2, part A. A unity feedback control system in the figure, question number 2a, gives an output response as shown in the figure. So this is the output response of that system in the time domain. So in the time domain we have this response. This is the steady state value, that is 0.8, and the overshoot is you can measure, it's approximately 1. So from here we can get its zeta. How we will get the zeta? From the first we will calculate the percentage overshoot. Okay, after percentage overshoot we will calculate the zeta from the formula, and we will also get angle theta by its cos inverse. So the corresponding root locus, its root locus is also given. So this is its root locus. One pole is at -1, -3 and -12. These are the open loop poles. Okay, so it goes to here. Okay, and this pole terminates at infinity, right? Okay, now question is, from the step response determine the damping ratio. So how will you calculate the damping ratio? I show its formula first of all. Its formula is this: percentage overshoot is C max minus C final over C final into 100. So C final is, your C final is 0.8 and your C max is approximately 1. So 1 minus 0.8 over 0.8. So percentage overshoot is equal to 1 minus 0.8 over 0.8 into 100, that is equal to 25%. That is equal to 25%. You have 25% overshoot. Now calculate its zeta. You also get some tables on the table. Some zeta tables are also available, on which you will get percentage overshoot and zeta and corresponding the angle theta. Like I show you a table here. Like this one is step response overshoot, its damping ratio and its phase margin. Okay, so sometimes it's given, sometimes it's not. So we will calculate this zeta from this with the formula, using the formula. Which formula we will use? We will use this formula: minus natural log percentage overshoot over under root pi square plus ln square percentage overshoot over 100. So put your 25 here. Okay, and then calculate zeta. It will become 0.4037. I did this with calculator. It's perfect, it's fine. Okay, and now take its cos inverse. If you take its cos inverse, you will get theta. Okay, so you will get theta, that is 66.19. so at 66.19 you will get the dominant poles. Like at 66.19 you will get the dominant poles, like here. You may also calculate with the software on here. You have to calculate it manually. So next part question is, from the root locus in the figure determine the dominant closed loop poles of the system. It means where the system is basically residing now, hence the gain k of the particular response. Okay, so the dominant poles will be theta at 66.19. so this will be around here, around minus 1.5. okay, and here this is near 3 point something. Here it is 3.2. here you can calculate, after calculating minus 1.5 plus minus 3.2j, so it's here in between. Minus 1.5 is your 1.5 is here minus 1.5 and 3.2j. okay, your system is approximately here. Okay, so now we have to calculate gain. Just put the formula k is equal to 1 over under 1 over modulus of g of s. What is g of s? This is g of s. And it's you can manually calculate it. It's s plus 1 into s plus 3 into s plus 12. so it will be s plus 1, s plus 3, s plus 12. Put this s here. So here minus 1.5 plus 1, you will get minus 0.5 plus 3.2j. Similarly here you 1.5 plus 3.2j and put here you will get something 10.5 plus 3.2j, and then multiply these three numbers and take its magnitude, you will get the gain. So this is the formula for calculating the gain. We started from percentage overshoot. We first calculate the percentage overshoot, right? C max minus C final over C final. C max 1 minus 0.08 into 100. We got 25%. Then from yes, from 25% we calculate the zeta. Okay. And then take its cos inverse. Cos inverse of 0.4037.
So we get the theta. Okay.
Theta.
And then on the theta we get the dominant poles.
Yes, exactly. You get the dominant poles. So when you get the dominant poles,
we got 2 poles.
Yes, 2 poles.
Okay, so which pole are we using as the S?
You can use any one. You can use one minus 1.5 plus 3.2j. Just use plus 1, plus only plus. One pole, use one pole here, put here, and then you will get the value of the gain. The value of the gain at this point. The system will have this gain 125.64. Your system is operating at this gain, right? This is the whole concept. Okay, so next part is hence the gain key for the particular response. Design a controller such that peak time can be set to 0.5 seconds with the same overshoot. Now you have the same overshoot, it's 25%, but your peak time, what was the formula of peak time? It was pi over omega d, right? It was pi over omega d. So you have TP pi over omega d equal to 0.5. So put take omega d here and 0.5 below, you will get 2 pi. So you get 6.28. You have omega d as 6.28. Okay, from this omega d and from this zeta, because zeta will be remains here because you have the same overshoot. The question said to you that you have to keep the overshoot same, so your zeta will remain 0.4037, but you have got omega d different. Your omega d is now different. From this different omega d, you will calculate omega n. Omega n, what is the formula of omega n? Its formula is omega d over 1 minus zeta square. This formula, this is very popular formula. This is used again and again. Here you can see that this is plus j omega n under root 1 minus, this is omega d. Basically this one is your omega d, and this is your zeta omega n, and this one is your omega n. Okay, so you are calculating your omega n from omega d and your zeta. Okay, so your omega n will be omega d over under root 1 minus zeta square. Omega d is 6.28 over 1 minus 0.4037. So you will get omega n of 6.86. Now calculate the new dominant poles. Now your dominant poles will be changed because your peak time has become 0.5 second. Your dominant poles will change. So what will be the new dominant poles? These will be the new dominant poles, minus zeta omega n plus minus omega d. So you can see here your new dominant poles. Yes, these are your new dominant poles, minus zeta omega n plus minus omega n under root zeta square minus 1. So here omega n will be now omega n, what is your new omega n? It will be your 6.86 multiplied by 0.4037. it will be the real part, that is 2.77. it's perfect written, I have checked it with the calculator. And plus minus omega n under root zeta square minus 1, this will be your imaginary part, or it's already here omega d. You can put simply here omega d 6.2. so these are your new dominant poles. So the new dominant poles equal to minus 2.77 plus minus 6.28 j. So design a controller such that the peak time can be set to 0.4 second. Now you have to move your poles of your system at this point, minus 2.77 plus minus 6.28 j. You have to move your poles at these points. So how you can move your poles at this point? You have to design a controller for this. You have to design a controller for this. So with the help of the controller, your root locus will pass through your new desired points, at which you will get this 0.5 second your peak time and your overshoot as 25%. So this is the standard procedure of the controller design here. This is your new dominant poles minus 2.77 plus minus 6.28 J, and your open loop poles are minus 1, minus 3, minus 12, minus 1, minus 3 and minus 12. Now how we have to proceed? We have to calculate the angles theta 1, theta 2, theta 3. It's standard procedure given in the Norman S. Nice book, and it's very well written here. Theta 1 is equal to 180 minus tan inverse 6.28 divided by 2.77 minus 1. Minus 1 the location of the first pole, minus 1. So 180 minus tan inverse 6.28 over 2.77 minus 1. After solving this, you will get 105.74. This is your theta 1. For theta 2, you have to calculate 180 minus tan inverse 6.28 over 2.77 minus 3. Here you will get 2.77 minus 3, the second pole, you will get 87.9. For the theta 3, you have 180 minus tan inverse 6.28 over 2.77 minus 12. Okay, you will get theta 3. So you will get 3 angles for each open loop pole, theta 1, theta 2 and your theta 3 for the new point, for the new root locus dominant pole from which you want your root locus to pass from these 2 points. Currently your root locus does not pass through these points. So if you want to pass your root locus through the new points to get the desired response, you have to design a controller, which you are doing now. So theta 1, theta 2, theta 3, you got these 3 angles. Now then you got theta z, the zero you are making the controller. Okay, theta z is equal to theta 1 plus theta 2 plus theta 3 minus 180. So add these angles and minus subtract 180, you will get theta z, that is 47.87. that is your the angle of the new zero you will design. And tan of and then another formula comes, tan theta z is equal to 6.28 over z minus 2.77. So here you put tan 47.87 and you make z minus 2.77 theta z, bring it down and calculate the z. So this will be the your location of new zero. So your controller, your PD controller, basically it's a proportional derivative controller. It will be s plus 8.45. This will be your controller transfer function. Okay, controller transfer function s plus 8.45. Now multiply this controller transfer function with your original transfer function, you will get your desired response. And now you calculate the gain. It's same formula for the gain. Take the inverse of the transfer function and it will be s plus 1, s plus 3, s plus 12 over. Why it's over? Because it's reciprocal. K is equal to 1 over cs. Here you can saw that your k is basically 1 over cs. For 1 over cs, this is 1 over cs. Okay, and this is how you get your desired value. Okay, so why it's in the denominator s plus 8j? Because it's in the numerator. In the original transfer function it's in the numerator, so it by taking its reciprocal, because it will be multiplied, gpd will be multiplied with g, and g is 1 over s plus 1, 1 over s plus 3, 1 over s plus 12. So k is equal to 1 over your transfer function, so it will become on the denominator and your denominator will become your numerator. So s plus 1, s plus 3, s plus 12, s plus 8.45. now your desired dominant poles are minus 2.77 plus minus 6.28. now take one from here plus with a plus sign, put it here, and if you put it here you will get k. So k will be your gain, that is your 54. Gain of the your PD controller will be 54. So your controller will be 54 into s plus 8.45. this will be your controller transfer function. This is a standard method for the your PD controller design, how you design a PD controller. Okay, the next part is discuss why any improvement is achieved in terms of steady state error when the control design part is added to the original system, hence provide the root locus of the compensated system. For the steady state, we have to make a lag controller or a PI controller to make the steady state error equal to 0. So to improve the steady state error, we have to add a PI controller. PI controller. So this is your P proportional and integral controller, K into S plus 1 over S. Okay, so K into S plus 1 over S. If you add this controller to your original control, that is 54.37 into S plus 8.45, this was the PD controller you designed earlier, just multiplied this with this controller. So your overall transfer function will be K into S plus 0.1 and S plus 0.81 over S. This is your for the PI controller S. So this will increase, this will your remove steady state error. So the total your transfer function will be 54.37 S plus 0.1 S plus 8.4 into S plus 1 S plus 3 S plus 12. So this is your overall transfer function. How is this is going to let me tell you the paint. Okay, this we have this transfer function and this transfer function and this output, right? And like this is plus minus. Suppose we can call it as a controller GC and we call it as a plant GP. So the overall transfer function will be the product of GC and GP, GC into GP. Okay, so GC, this we designed earlier, like K into S plus your the term here, what was that? It was 8.45. It was 8.45, 8.45, right? And then we added another controller, the KI controller S plus 0.1 PI controller S. Then we multiplied this with the GP. What was GP? That was 1 over S plus 1 S plus 3 S plus 12 S plus 12 rest. So this will be the overall transfer function. So with this transfer function, you will get zero steady state error and improved transient response like TP 0.5 second and overshoot of 25%. So this is the controller design, typical controller design problem. Okay, so these are two parts, part A1 and part 2, 3, and part B we have completed it. So this concludes our question number 2. Thank you. So the previous root locus was your S here, S plus 1, S plus 3 and S plus 12. Now you have S plus 0.1, S plus 8.45 and S here. So you have one S here, one pole here at the origin, okay, and two zeros at minus 0.1 and minus 8.45. Okay, so here you can see that this pole and 0.1, this pole will be added to this 0. Okay, odd number, 1 is odd number, so there is root locus 1, 2, there should not be any root locus, 3, yes, there should be root locus here. So here you can see that minus 1 minus 3, it goes like this. Okay, and then you have a 0 at 8.45 minus 8.45 and then minus 12. This pole will be ended up here. So 1, 2, 3, yes, 4, 5, yes, we have the root locus on the odd number, on the left side of the odd number of the poles or zeros. So this is your new root locus. This was your previous root locus. With the controller, by adding your PI and PD controllers or a PID controller, your root locus will become like this. Okay, this is your revised root locus controller, and its benefits are good peak time, 25% overshoot, and 0 steady state error. So this is the last part. Has provide the root locus of the you also said that it is a compensated system or controlled system because you have added some controllers in it. Okay, so this will be you have added some compensators, both lead compensator as well as lag compensator. Your PD compensator is basically a lead compensator. This is a lead compensator, and this is a lag compensator. You have added both in it, and together it becomes a lead lag compensator or a PID controller in it. Thank you.